TikTok craft. I am super late to TikTok. I haven't dived. I haven't gotten into TikTok yet. I don't know. I just don't feel like it. I already have enough social media. Ugh, my hands cramp too bad. I can only do so much stuff like by hand. I don't know if I'm pre-arthritic or whatever, but yeah, my hands cramp really bad. Like if I like am mixing stuff for a long time. So so I don't know if I could ever do a full on bakery, Isaac. Yes, Anna playing the Minecraft. I'm glad you're enjoying Minecraft, Anna. TikTok is controlled by China. Naya with the conspiracy theory. I've heard good things about Doom Eternal. No, Isaac, yeah, no, I know. I just, I don't know if I have a favorite thing. I always jump around between different stuff. The only thing I really make consistently are chocolate chip cookies. My favorite thing to bake is something I've never baked before, which is kind of an interesting answer. See, but that's the thing, because I always just make new things. So I've always gotten compliments on a lot of things. I just, yeah. Oh, true. I forgot as well. If we ever actually go back to school, I'll make you guys cookies. How's that? Cookies for AP. Nice, Sammy. All right. Let's get into it. Let's get into it. I don't know if I've ever made tiramisu. I don't love coffee. Nice, Max. All right. So what we're going to do, how's this going to look? So if you remember for the calendar, what we're going to be doing on Monday and Wednesday, we're going to be doing reviews, right? So we're going to be doing content reviews. I'm not really going to be doing like, because I changed them to be valence electrons, Logan. You can customize a lot of things. I'll be customizing and changing things. No, a lot of people love tiramisu, Isaac. Okay, so what we're going to be doing, right, is we're going to be going through all the units on the AP curriculum, at least all the ones that they're going to do on the test. I took a survey on Friday. They got my input on like when they should offer the test. So it looks like they are going to be offering the test at a later date. And so I that first week in May isn't going to be our deadline, right? So I think we're gonna have more time to take the exam, so don't feel super time crunched. So this will be good. So we're gonna go through the units. I'm gonna do the notes. Most likely not Isaac. I'm gonna do kind of just like a concept review. I'm gonna answer questions as you guys have questions, and then we're gonna use Fridays to go through the actual problems from the AP free responses. So remember, you've got free response due Thursday night. So the way class runs: notes Monday, Wednesday. Free response due Thursday night. On Friday, we'll go through the answers for the free response. Bryce, that's an up to you question. I mean, I am going to be writing stuff down. Whether or not you want to take the notes is up to you. I think it would be beneficial, but again, you don't have to. So I'm not going to be grading them or doing it like that. Yeah. Okay. Notes Monday, Wednesday. Free response every week to Thursday, except next week, spring break. And then we'll go over the free response on Friday. I will grade the test from last night tomorrow. And so if you have any questions on that, we can go over that then. If you didn't do the test last night, I haven't looked at it yet. I'll double check and maybe reopen it for you, and I'll send you a message or something. So we do have one this week. The free response is already up on Canvas. It's already up on Canvas. It's due Thursday night. That's okay, Naya. We'll figure it out. Yeah, so the free response is already on Canvas. It's on the modules. So yeah. So if you're skipping all of problem 1 for this one, it should still take you somewhere around an hour, maybe a tiny bit longer, but I would shoot for about an hour. Yeah, so doing it on Tuesday, like tomorrow, or doing it Thursday when we don't have class, that would be a good time to use that time to do the free response. But I want to have it done and turned in by Thursday night. And we'll talk about how to turn it in and grade it later, so don't worry about that right now. I don't know, Haley. They're shooting for 45 minutes, which means that so typically you have 105 minutes, so they're basically like basically cutting in half. Oh, the school's calling me. So what they'll probably do is they normally do 3 short and 4 long. Or sorry, 3 long and 4 short. My bet is they're probably going to do like 1 long and a couple shorts. I actually have no idea. The format, they're going to come out with the format later this week. So they'll let us know later this week what the format of the test is going to be. So we can talk about that hopefully Friday. If not Friday, maybe I'll send you guys a message about it. Okay, let's get into it. Roman numeral 1, Unit 1. So we can call this AP Review. Roman numeral 1, Unit 1. Letter A. Yeah, so I don't know like what time it's going to be released on Friday, so we'll have to see. If it's like up as soon as Friday hits, then we'll talk about it. If it's not until Friday afternoon, we'll maybe have to wait till later. All right. We're starting simple, right? First thing, the mole. Okay, that is the very first thing AP Chemistry decides to start with, the mole. Okay, so number 1. Nice, David. Good to see you in the chat. So the mole, we're going to start with basically it's the first thing is factor label. That's not how you spell label. Factor label. I can spell. Okay, so we're going to do factor label. That's the first idea. That's the first objective is how can you change grams into moles? How do you change moles into grams? Right? So, key thing here, Avogadro's number. .022 times 20 to the 23rd things, usually atoms, equals a mole. Yeah, it's been a while since we've done simple conversions. Okay. Yeah, my factor label looks funny. I'm sorry. I should probably just scratch it and rewrite the whole thing, but it's what's done is done. So David, that's a great question. So this number has actually been refined over the years. Originally, it was 6.03 times 10 to the 23rd. Like the experiment Avogadro did is he measured various gases and he attempted to figure out how many molecules were in a mole, and it's relating the grams using the atomic system to the grams that we actually measure. So it is experimentally determined. Avogadro, if I remember correctly, used experiments with gases and measuring exact like quantities of gases collected, and then some fun math. Okay. Good. Okay. So letter B. So if you have 1 mole of atomic mass units, aka AMU, equals 1 gram. Okay, this is why we can use the weights on the periodic table and we can convert into grams. Okay. Right, so this is how we do the idea that 1 mole of carbon is 12.01 grams. Right? Because on the periodic table, carbon is 12.01 AMUs. And so if we have a mole of carbon atoms, it's going to be 12 grams. This is really simple because this is, of course, the foundation for so many things that we're going to do later. Right? So we're starting simple because we're starting way back at the beginning, Unit 1. Okay. Cool. Again, and because we've done all this, I'm not going to do any like examples of anything. Yes, Isaac, we're going to do 1 Roman numeral per day. There's 1 unit that's like huge that'll take us 2 days, but yeah, 1 Roman numeral per day. Yeah, Unit 3. That's the one that's huge. Yeah. Yeah, Unit 3 is like twice as long as any of the others. Okay, let's go to number 2. We need to talk about mass spectrums. All right, so mass spectrums let me angle this. All right. So if you remember, a mass spectrum was kind of a graph, right? That looked a little bit something like this, right? So on our y-axis, we have percent abundance. And on our x-axis, we have mass. Okay. What am I improving? I don't even know what I improved. So on our y-axis, we have percent abundance, and on our x-axis, we have mass. Okay. So what we would see on this is you would see something like, maybe something like this. Oh, my whiteboard. Yeah, you like my whiteboard? Made out of my 2 sheets of paper. All right, so we would see a mass here. Now, if we say that this peak is at 35 and this peak is at 37, okay? So what conclusions can we draw from this mass spectrum? First thing we can draw is how many isotopes are there of this element? Okay, so a mass spectrum shows the mass of an element with the percent abundance. Okay, so how many isotopes are there? Oh yeah, there's 2 isotopes, right? So of this element, there are 2 isotopes. Okay, so let me do a little small Roman numeral. So peaks equal isotopes. Okay. Now, what do the heights of those peaks tell us? Ah, we're getting there, Maggie. We're not there yet. Yeah, so they tell us a percent abundance. So of our two isotopes, which one is more abundant? Yeah, the 35. Okay, so let's scroll this up. So let's say, so the taller peak equals more abundant. Okay. And the average mass is a weighted average. Okay. What do I mean by a weighted average? Do I just average 35 and 37 to get 36? No, okay, good. So we have to take into account the percent abundance. Thanks, Mary. So we have to take into account that there's a greater percentage of 35 and there's a smaller percentage of 37. We could actually do the math on it if we wanted to. It's closer to 35. Okay, so which element is this? Maggie already said it a little while ago. Yeah, it's chlorine, right? This is chlorine. Chlorine has an average mass of 35. If you look at a periodic table, okay, if you don't have a periodic table up, right? If you look at a periodic table, chlorine's average atomic mass is 35.45. Okay, it has two isotopes, chlorine 35 and chlorine 37. And so the average is closer to 35 because the chlorine 35 is more abundant, right? So all of that information that we have on the periodic table can be shown in a mass spectrum graph. Okay, so make sure you're comfortable reading with and looking at a mass spectrum graph. Because these are kind of the big three takeaways. The peaks tell you how many isotopes there are. A taller peak is the more abundant isotope, and then the average mass is the weighted average. Okay. Any questions about mass spectrums? So if you were actually given the values, so that's a good question, Max. Check something. All right, so for chlorine, right? Chlorine is we'll just say 75.8% chlorine 35, which weighs 34.97 AMUs. And it is, what would that be, 24.2% chlorine 37, which weighs 36.97 AMU, right? So how would we, if we actually had this information, how would we calculate the average atomic mass? Or if this graph was more drawn to scale, you would be able to interpret these percentages from the heights. So the average, right? We would take the percentage as a decimal, so 0.758 times the mass, 34.97, plus the percentage as a decimal, 0.242, times 36.97. Okay. So yeah, you just multiply by the percentages and add. So the easiest way is to change the percentage into a decimal, multiply by the mass, and then add them all together. And if we do this, it should equal 35.5. Ish. I'm sure it will, but or 35.45.4, something like that. Okay, so if you ever asked to actually calculate it, it's percentage times the mass, add them all together. No, Isabel. The free responses every week are going to be cumulative. They're going to be everything. So it'll be stuff that you will probably be like, I don't remember how to do this. So yeah, the reviews will kind of be, it's kind of like we're going in two paths. We're doing the physical reviews, and then we're doing the questions as kind of a side thing. So the questions, that my hope is that every week those free response questions should get easier and easier, and you should get more and more comfortable. This first one's probably going to be a little rough. Okay. 35.454. Apparently, Isaac actually calculated it. Proper sig figs. I think I only have 3 sig figs in this percentage, so 35.5. Cool. Yeah, just gonna be completion, Bryce. I really just want you guys working on this and doing it. Again, you're gonna get out of it what you put into it is kind of the idea. All right, so let's see, that's that. I'm gonna need more paper. Okay, so we have the mole, we have factor label, mass spectrum. Let's go on to our next thing. So the next letter, big letter. So jump out, big letter B. Big letter B, chemical formulas. All right, so number 1. Pure substances. Little letter A. Yeah, naming compounds, pretty much, Isaac. Naming compounds is part of this. There's a lot of stuff in this. So this is also like, so we can talk about molecules and formula units, aka covalent and ionic. So when we talk about mass spectrums was number 2. So letter A, number 2, mass spectrum, big letter B. All right, so chemical formulas. So molecules and formula units, aka covalent and ionic compound. Basically, we have formulas, right? Molecules and compounds have formulas. We have the law of definite proportions. Definite proportions. And the law of multiple proportions. So if we remember, our law of definite proportions says that every time you have a compound, if it's the same compound, it has the same elements in the same ratio. So for example, sodium chloride salt will always be 1 part sodium, 1 part chlorine. It will always be 23 grams of sodium for every 35.5 grams of chlorine. That is definite proportions, right? And then if you have water, of course, water is always going to be H2O. It's always going to be 2 grams of hydrogen for every 16 grams of oxygen. So your formulas the elements mix in definite ratios. Yeah, so this was Lavoisier. Well, Lavoisier was conservation of mass. We had Proust, who came up with definite proportions, and then Dalton was the one who came up with multiple proportions, right? So Dalton, again, used this to come up with atomic theory, which we're going to get to a little bit later. And so the idea, right, with multiple proportions, you can have the same elements mixing in multiple ways to make different compounds, right? So H2O versus H2O2, water versus hydrogen peroxide. Your same elements can combine in different ways, but that's okay, okay? So, number C here, compounds are the So compounds are the simplest whole number ratio. Technically called an empirical formula. Okay, so not all compounds are the simplest whole number ratio, but when we talk about like ionic compounds are always in the simplest whole number ratio. When we talk about covalent compounds, the simplest whole number ratio is known as an empirical formula. And so when studying and learning about compounds and what a pure substance is, it's always going to have some sort of an empirical formula, which is the simplest whole number ratio. Somebody's writing some music. All right. So this is where we get like percent composition problems. Man, my skin looks really yellow under the camera. I wonder why. Anyway, we get these percent composition cameras or percent composition problems where you say like, oh, this compound is 6% carbon, 12% nitrogen, 38% oxygen. What's the empirical formula? We'll maybe do some of those as they come up, but I'm not going to do that here or now. Okay, number 2. Mixtures. Sorry, I'm just checking my notes. So a mixture is it's a mixture. So we have 2 or more substances mixed by varying percentages. Right? So mixtures don't follow the law of definite proportions or the law of multiple proportions. In a mixture, you can have it could be, you could have one mix that's 20% sodium chloride and 80% sodium bicarbonate, or you of course could mix it up and have 10% 90%, 5% 95%, whatever. Mixtures don't have to follow the same ratio because they are a mixture of different things coming together. Compounds always have to follow the same percentages because they're compounds. And then we can do, of course, there's all kinds of analysis. So analysis can be done to determine purity, right? So you can actually determine whatever the purity is of your substance by doing some sort of analysis. Now, we've done a bunch of labs that have looked at trying to determine purity. A lot of the lab problems we've done have all been about figuring out how much of a mixture is an impurity or how much is pure, and we do that by titration, gravimetric analysis, all these other experiments. We'll have a day where we talk all about experiments and experimental design and things. So for now, just analysis is used to determine composition or purity. Okay. Shoot, am I out of notes? I might be out of notes. I need more paper. I've got a couple of blank pages here. Might work. All right, so that's chemical formulas. Okay, big letter C. Electrons. All right, electrons, number 1. Hey, what's up?
Just hiding stuff.
Oh, from children? All right, what do we want to say about electrons? We want to say that she's gone, Lauren. I'll tell her you said hi. Okay, so we want to say that electron configurations is our first thing here. Oops. All right, so do we remember electron configuration? One is 2, 2 is 2, 2p6, 3 is 2, etc. So the first thing we have to the first thing we have to remember. Okay, some of you know, some of you yes. The first thing we have to remember is that an atom is it's a positive nucleus with protons and neutrons. Surrounded by negative I can't write that. Okay, negative electrons. Okay, so it's an atom is a positive nucleus with protons and neutrons surrounded by the negative electrons. Okay, 2 types of peaceful, Isabel, exactly. Okay. And then what we want to do, I didn't really make a big emphasis about this as we go through the class, but the AP test loves Coulomb's law. Sorry. So Coulomb's law, C-O-U-L-O-M-B, Coulomb's law. So Coulomb's law basically says that the force between 2 charged particles is equal to or proportional to Q1 times Q2 divided by R squared. Yeah, it's physics, right? Now you're never actually going to plug into this equation. You just need to understand this equation conceptually. Okay, so the Q is the charge. R is the radius. And F is the force. Okay, so basically what it's saying is that if you have 2 charged particles, the greater the charge, the more attracted they are to each other. Right, so if you have like +2 and -2, that's going to be a greater force than +1 and -1. And then it's also a function of the radius, the distance between them, right? A smaller radius, if we think about this, radius is on the bottom, a smaller radius results in a greater force. A longer radius results in a lower force, okay? Now, this idea of greater charges is stronger and smaller radii is stronger, we've been talking about that all along. We've been inferring and referring to Coulomb's law. I just haven't called it Coulomb's law. So understand, if they ever throw Coulomb's law at you, the idea with Coulomb's law is it's just force is charge and distance. Greater charges, smaller distance, stronger force. That's all you need to know. Okay. Okay, so we can talk about electron configurations. So let's just talk about maybe just oxygen. So oxygen is 1s2, oops, 2s2, 2p4. Okay, now what is the 1? What is that idea of a 1? What is that? Oh, there should only be, Naya, there should only be ads as you like join the channel. If you're watching it, it shouldn't cut for ads. Is it cutting for ads? It should only make you watch an ad as you reload the page, or if you like first come in. And that's just Twitch. That's how they make their money. Oh, okay, yeah, Naya. So yeah, so Twitch has to make money somehow. So they're giving this free service. So when you join into the channel, it might give you like a 15-second, 30-second ad or something. So yeah, energy level. So Mary, we can call this energy level. Some people also use the term shell. So if you see the term energy level or shell, that's what we're talking about. Okay. You can also, and then with, like the P, okay, we can call P either of course, our specific orbital, or some people call it, we can call it a sublevel, or some people call it subshells. Okay, so when you say you have a 2p4, that means that there are 4 electrons in the 2p sublevel, right? And that's talking about the second energy level. Okay, so the number out in front, the principal quantum number, that's our energy level or shell, where when we talk about this s orbital and this p orbital, those are sublevels or subshells. So just make sure you guys are used to the terminology: energy level for the number in front, sublevel for describing the specific 2s or 2p. We also have the designation, at least for oxygen, we have on the left side here, we have core electrons, and then we have valence electrons. Right, our valence electrons being those in the higher energy level, the highest energy level. With oxygen, the second energy level is the highest energy level, and the core electrons are those in the sublevel, or sorry, not the sublevel, but are in the lower energy levels. Okay, so we have core electrons, these 1s2, valence electrons, 2s2, 2p4. This is art by my children. 1s will always be core electrons, Austin. But if we go into a higher energy level, we could also start to include like the 2s. So little letter d. Yeah, because if we were looking at like phosphorus or sulfur, chlorine, right, anything on the third energy level, all the electrons in the first and second energy level would be core electrons, and the electrons in the third energy level would be the valence electrons. So yeah, 1s will always be core, Lauren, unless it's hydrogen or helium. Yeah, I was about to say, unless it's hydrogen or helium, then hydrogen and helium, those are their valence electrons. Yeah, good catch, Ascon. Okay. Letter D. Isaac, it's whatever works for you, man. Whatever works for you. If you are an underline person, if you like underlining things, if you're a highlight person, if you like sticky notes, whatever system you want to come up with is fine with me. All right, let's look now at ionization energy. Right, so real quick, what is ionization energy? Energy needs to ionize. Yes. But yeah, when we talk about ionize, we're talking about removing electrons. And so it's the energy needed to remove an electron. It's to form a positive ion. Okay. This goes back to Coulomb's law, right? We have to worry about the charges and the radius. So since electrons are, all the same charge, they're all -1, core electrons will always have a higher ionization energy than valence electrons because they're closer in terms of their radius, right? So because the radius is smaller between your nucleus and a core electron, it's more difficult and takes more energy to remove a core electron than it does to remove a valence electron, which is going to be out further, okay? The other thing too is as you add more and more and more and more electrons, as you get bigger and bigger and bigger atoms, the nucleus becomes more and more and more positive. So as your nucleus gets more and more positive, it also becomes more difficult to remove an electron. So David, that's an interesting question. Not really. So when we talk about removing an electron, if you're just trying to remove just one electron, it's a lot easier to just pluck off a valence electron. Now, if you take a sample of an atom and you blast it with X-rays, technically you could rip out a core electron before removing a valence electron. But it's like a probability thing, because you could also just remove a valence electron. It just depends on how that X-ray interacts with the atom or the sample that you're shooting it at. So, yeah. Hopefully that answers your question. Okay, so energy to remove an electron, again, radius and nuclear charge are key ideas here. Okay, cool. Number 2 on electron configuration, or on electrons. I'm glad your dad is listening in. Okay, so number 2. Let's talk about photoelectron spectroscopy. Also known as PES. Okay, do you guys remember anything about photoelectron spectroscopy? We did a Poggle! Isaac remembers the Poggle. Yeah, we did a Poggle. Okay. So, a photoelectron spectrum, the way it works, the way it looks, it's going to look something like this, usually. So it'll look something like we'll have, you know, like probably a peak like this, and then like usually like a break, and then a peak like this, and then a peak like this. 1, 2. And then some sort of a break, and then maybe a peak like this. Okay. So again, we have abundance on the y-axis, and then we have energy on the x-axis, but this is usually called binding energy. And these graphs are usually oriented so that 0 is out here, and then this is like some big value, like 10 megajoules or something. I'm just making something up. We'll just say it's 10 megajoules. Okay, so the y or the x-axis is oftentimes reversed. Okay. So what did, if you remember, what a typical photoelectron spectroscopy experiment is they take a sample of a gaseous atom and they fire X-rays at it, or they fire a tunable laser, and then they measure the kinetic energy of the electrons that are ejected. And by taking the amount of energy they put in and subtracting the amount of energy they get out, they can determine the binding energy. In other words, how strongly bound the electron was. So really, this is experimental evidence for this 1s2, 2s2, 2p4 idea. Okay, so if we look, okay, if this was an atom, okay, which electrons are the most tightly bound? Which electrons are going to be the hardest to remove? The ones closest to the core, which are the 1s electrons. So we can actually label this first peak as 1s, because these are going to be the hardest electrons to remove. Okay, so then if these are the most difficult to remove, which ones would be the next most difficult to remove? It'd be the 2s, right? So this peak we can label as 2s. Whoa, this peak's so much higher. What would this peak be? 2p. And then lastly, this peak would be... I know, it takes a couple seconds. 3s. Good. Okay, so if we were to write down the electron configuration for this element that I've drawn, this element I've drawn is 1s2, 2s2, 2p6, 3s... Now, wait a minute. The height actually tells you how many electrons there are in that subshell. So that's why it's 3s1, Logan, because it only goes up half as high as the 1s and 2s do. So the height tells you how many electrons are in that subshell. So 1s2, 2s2, 2p6, 3s1. So then what element is this? Oh, if you're lagging really bad, reload the page. All right, So 1s2, 2s2, 2p6, 3s1. It is sodium. Thanks, Austin. Right? And you can tell that by looking at a periodic table. Sodium is going to be in that 3s1 spot. Okay. Oh, good. I'm glad. If you've watched an ad in the last, or you might have an ad block, who knows? Okay. So 1s2, 2s2, 2p6, 3s1, sodium. So this is pretty much all you have to take away from our photoelectron spectroscopy. The highest energy electrons are going to be our core electrons. The lowest energy electrons are going to be the valence electrons. The height is relative to the number of electrons in that subshell. Cool. Any questions about photoelectron spectroscopy? Okay, doesn't sound like it. Cool. This leads us to letter D. Let's see if I can do. I should be able to do this one fast if I can find paper. No, I don't have any more paper. Oh, good. Letter D. Periodic trends. Oh, did we already do D? Letter E. Thanks, Max. Periodic trends. Okay, we're almost done. I'm going to try not to go late. Okay, so periodic trends. No, it is letter D. Dang it. Letter D. Yeah, this is big D. No, you're good, Max. Sorry. All right, so periodic trends. Our periodic trends, we've got... okay. So first thing we need to talk about in periodic trends is the periodic law. I've been fooled by the old razzle dazzle. Periodic law. The periodic law says that when elements are arranged by increasing atomic number, there is a there's a regular repetition of properties. Yes, good old Dmitry Ivanovich Mendeleev. Hey, thanks for the follow, Vargan. Appreciate it. That was an hour ago, though. Anyway, so periodic law. When elements are arranged by increasing atomic number, there's a regular repetition of properties. Okay, so let's just look at our periodic table, right? So we said there's a couple things. So if you remember a periodic table, okay, what are our trends as we go from left to right? There are 3 of them. We've got radius, ionization energy, and electronegativity slash electron affinity. Okay, so as we go left to right, radius, ionization energy, electronegativity, and electron affinity. what happens with radius? As we go from left to right, what happens with the radius? It decreases. Right? As we go left to right, the radius decreases. And the reason why the radius decreases is because we're getting more protons in the nucleus, and the electrons are adding to the same level. Right? So the electrons are adding to the same level. No, it's going to get smaller. Right? Ionization energy, on the other hand, ionization energy goes up, and electronegativity and electron affinity both go up. Yeah, so we said helium, right, has our smallest radius because as we go down the periodic table, radius increases, ionization energy decreases, and so does electronegativity and electron affinity also decreases. No, you're good, Sammy. You're good, Sammy. So, as we go from left to right, our radius decreases. Ionization energy, electronegativity, and electron affinity all increase. As we go from top to bottom, the radius increases because we're adding new energy levels, new shells, and our ionization energy, electronegativity, and electron affinity all decrease because that outermost electron is getting further and further away from the nucleus. All right. So last thing, same group or column, similar properties. So, oh, good. Yeah, good, Haley. I should have reminded this. Electronegativity is how much an element pulls on the electrons in a bond. So the stronger the electronegativity, the more that it pulls on new electrons. And then electron affinity is how much energy is released when an atom gains a new electron. Yeah, so when we say group, we could say the same family group, all those things. And the reason why they react that way is because they have a similar number of valence electrons, Isaac. Okay. But it is 11. I've kept you guys long enough. This was a good Unit 1 review, right? So that's everything you need to know for Unit 1. We have, what, 6 more to go? Good night, Philip. Enjoy your sleep. Okay, so I'll get this. Let's see. Don't the reactions get more extras going on? Yeah. So things change, right? And that has to do with the fact that the ionization energy decreases. There's all kind of things because technically with nonmetals it gets more reactive as you go up, but with metals it gets more reactive as you go down, and that just has to do with what properties we're actually looking at. So yeah, Isaac, there's a lot of properties that can. There's just a lot of interchange that we just have to. There is a trend. Short answer. Okay, I'll be in the Discord at noon to answer any questions that you guys might have as you're working through the short answer. I have some interviews I have to participate in. We're hiring a new biology teacher next year, and so I have to be involved in the interview process. We're going to do it over, I think, Zoom or Google Meet or something. So we've got a potential. Well, no one's leaving. We just are getting. Brighton has like 100 new students. And so because we have new students, we have to hire a new teacher because we don't have enough teachers. So we're hiring a new biology teacher. So we're interviewing for that. Yeah. So we're interviewing for that this year or this afternoon. So I'm sure we'll get some good ones. Yeah, Nair, you're right. Our regular bio classes are already busting at the seams, so we definitely need a new biology teacher. Okay, good luck. Work in your review packets, or not your review packets, in your review books. Do the short answer when you get a chance. We'll be doing more review on Wednesday. You guys enjoy the rest of your afternoon, and we'll see you on Wednesday. Not tomorrow, Wednesday. Bye, guys.